Hello all and welcome to week number 7 of the course Fundamentals of Electrical Engineering. And as usual, first let's go through the summary of last week. So basically in the last week we started the chapter of circuit theorems, in which we discussed two theorems, superposition theorem and source transformation theorem. And we discussed that superposition theorem says that uh, as per the linearity principle, the voltage or current at any branch or through or across any element can be measured as the sum of contributions due to each independent source, right? So this is the statement of superposition theorem, that the voltage across or the current through any element in a linear circuit is the algebraic sum of the voltage or current due to each independent source acting alone. We also covered 2 or 3 examples of superposition theorem, and then we moved on towards the source transformation theorem, which focused on the interconversion between a voltage source and a current sources. And we also discussed that not every voltage source can be converted into a current source and vice versa. Certain criteria needs to be met so that the interconversion is possible. And we discussed that if a voltage source has a series resistance, then we can convert it into an equivalent current source with the same amount of resistance in parallel, and vice versa is also possible. That is, if a current source has a parallel resistance, then it can be converted into an equivalent voltage source in series with the same amount of resistance, and the magnitude of the voltage is calculated by Ohm's law, that is V is equal to IR. Voltage is the product of resistance and current. So I hope it is clear now. We discussed these laws in the last week's lecture, and we also covered a few examples of both the theorems. So coming towards the overview of this week, in this week we will be covering 3 theorems majorly. First one is the Thevenin's theorem, the second one is the Norton's theorem, and the third one is the maximum power transfer theorem, right? So Norton's theorem, first we will discuss Thevenin's theorem, and then we'll move on towards the Norton's theorem. What does Thevenin's theorem say? And even before studying Thevenin's theorem, let's discuss the significance of this theorem. Let's talk about a household electricity network or a common network where we have a source, a generator, that can be AC source or a DC source, right? We have a generator, and then after that we have transmission lines, and after the transmission lines we have the grids, and then finally supply comes to our households, where we have a distribution board. After distribution board we have wires, and then finally we have a room socket, right? So what this results in is that the load in the room socket is not fixed. Sometimes we just plug a mobile charger in the room socket, whereas sometimes we may plug an iron in a room socket. Sometimes we may plug a pedestal fan, and sometimes if it is a kitchen socket, we can even plug a fridge or a microwave oven, right? So basically, if we analyze the circuit, then from the generation end up to the load terminals, all the resistance, all the circuit scenarios are same. Just the load is changing. And if I need to analyze the circuit, and let's suppose that it is a very complex circuit, right? And I start from the generator side, and there is a bulb connected to the circuit, right? I start from the generator side, perform on the analysis, and finally there is a bulb. So I calculate the voltage and power of that bulb, right? Okay, this is the value of V and I. And then I also need to analyze my circuit with a microwave connected to it. Then again I have to do the same things. And let's say for a third time we have a pedestal fan connected to it. Again I have to do the same thing, analyze the circuit right from the generator, then the transmission line, then the cable, then our household distribution, and finally the socket. So here what you analyze is that the majority of the circuit layout is same, just the load is changing. And this is where our Thevenin's theorem is really beneficial. What this theorem focuses on is the simplification of a circuit, except for the load terminals. What this theorem will do, this theorem will leave out the load terminals, and other than the load terminals, all of the circuit will be simplified. We will see that, right? So what does this theorem states is that any complex linear two-terminal circuit can be represented as a simplified network having a voltage source of magnitude V Thevenin in series with a resistance of R Thevenin, where V Thevenin is the open circuit voltage across the load terminals and R Thevenin is the resistance of the network as seen from the load terminals when all the independent sources are turned off. First of all, let's talk about what is Thevenin's theorem, right? If I can draw it like this, so this will be my Thevenin's theorem. There will be a voltage source with polarity positive and negative, right? Then there will be a series resistance, right? And finally we have a load terminal or load box where we can say that the load resistance is connected. This is RL, this is V Thevenin, and this is R Thevenin, right? Now, what you need to analyze is the importance of this theorem I was talking about. Now, let's say that the load changes, the resistance changes. Now we have a microwave oven connected. Here you can simply see that it is just a single mesh and you can quickly calculate the current through it. Now the load changes and in place of RL we have a bulb connected. Again it's a single mesh. You can easily calculate it. So basically the complex nature of the circuit is reduced. What you have done that from the generation up to the load terminals you have simplified the circuit, and that circuit which included multiple loops, multiple nodes has now been simplified in this format such that it has a voltage source and a series resistance and there is a load connected. Now it doesn't matter if how much the load changes, we can easily calculate the current. What will be the current? I will be equal to how much? V Thevenin, right, divided by R Thevenin plus RL. Why? Because R Thevenin and RL are in series, so it is very easy to calculate now. Instead, previously if we had 2 or 3 loops, it was very difficult. All the time we have to form the simultaneous equation. So this is the significance of this theorem, right? And this is what we are talking about, that why Thevenin's theorem is very important. And the converse of it is Norton's theorem. But first, let's move on towards a few examples of Thevenin's theorem, and then we will look at the Norton's theorem, right? Well, let's now move on towards the first example of Thevenin's theorem, and the question says that find the Thevenin equivalent for the circuit shown in given figure. Find the Thevenin equivalent for the circuit shown in given figure. This is part A of the question, right? And the next part says also find the current through RL, that is the load resistance, when RL is equal to 6 ohms, RL is equal to 16 ohms, and RL is equal to 36 ohms, right? So this is a statement of our question. And first of all, since we know that we are going to find out the Thevenin equivalent of the circuit, so let me draw the circuit first. We have a 32 volt source, and then we have a 4 ohms resistance, and we also have a 12 ohm resistance here, right? And then we have a 2 amperes source, 1 ohm resistance, and then we have this value of RL, which is the load resistance, and it is continuously changing, right? So this is the layout of our question. So coming towards the first step of the question, the very first step that we have to do is to open the load resistances. These are the load resistance terminals. So the first thing that we need to do is to open the load resistance terminals, right? So when you open the load resistance terminals, then your circuit will become like this. This is the 32 volt resistance, and this is 4 ohms, and then we have the 12 ohm resistance, and finally we have the 2 ohm source, 2 ampere source, and the 1 ohm resistance, and these terminals will be open circuited. Now one thing you people must note, that since the terminals have been opened, so the voltage across these terminals will be the Thevenin voltage, right? Because the definition says that Thevenin is basically the voltage across the load terminals when they are open circuited, right? So now one thing we need to check, or rather we need to understand, is that when these terminals are open circuited, there will be no current through the 1 ohm resistance, right? I am repeating it again, that once these terminals are open circuited, then the 1 ohm resistance will not bear any current, which means, now this is very typical, please understand it carefully, which means that the voltage that is appearing between the load terminals will be the same as the voltage appearing at this node. Let's name it as node A, node B, node C, and node D as the reference node. Now the important thing is that the voltage VC is equal to the voltage VB, and this is the Thevenin voltage. And why this is the case? Because since we have open circuited the load terminal, so there will be no current through the 1 ohm resistance. And since there will be no current through the 1 ohm resistance, which means that the voltage between VB and VC will as it is appear at point VC and VD. VB and VD, the voltage will be the same as VC and VD, and this is actually the Thevenin voltage, right? I am once again repeating it because it's a bit typical, that the first step we need to do, basically we need to simplify the circuit, and we need to find its Thevenin equivalent. After that we can easily find the current, no issue with that. So the two things that we need to do, the first one is to find the Thevenin voltage, and the second one is to find the Thevenin resistance, or it can be in the reverse manner also, no issue with that. But what is the Thevenin voltage? It is basically the open circuit voltage across the load terminals. First you need to open circuit the load terminals, that we have already done, and then the voltage which appears across these load terminals. This is basically the voltage we are talking about as the Thevenin voltage. And since these terminals are open, we know that through an open circuit there is no current. The current is zero. So the current through 1 ohm resistance will also be zero. And since the current through 1 ohm resistance will be zero, then it means that the voltage of node B, VB, will be equal to the voltage at node C. The same voltage will appear. And that is actually the Thevenin voltage, right? So now let's solve the circuit. There are different methods for solving the circuit. We can see that we can also solve the circuit using nodal analysis, perhaps, and that will be the most easiest option because there is no node as node C. Why? Because these are the same nodes effectively, because there is no current through this resistance. So we do not need to consider this part, right? We can effectively consider this part of the circuit and apply nodal analysis to it, right? So we know that there is a voltage source present between a reference node and a non-reference node that makes the source voltage equal to the node voltage, which means VA will be equal to 32 volts, right? And then we can simply calculate the value of current here to apply nodal analysis. So let's apply nodal analysis, and the equation will become applying KCL to node B. Let's name it as current I1. This will be current, this won't be any current because this is the same node. This will be current I2, right? So here we can see that the current I1 is entering the node, so it will be taken as positive. The current I2 is leaving the node, so it will be taken as negative. And then we also have a 2 ampere current entering the node, so that will be taken as positive equals to 0. When we convert this I1 current in terms of voltages, here we can see that it is leaving node A. So VA minus VB divided by 4, or in other words you can say that it will be 32 minus VB divided by 4, right? Minus I2 will be what? VB minus 0, that is VD, divided by 12. So it will be VB divided by 12 plus 2 is equal to 0, right? So it will be 32 divided by 4, 8, minus VB divided by 4, minus VB divided by 12, plus 2. 8 plus 2 is equal to 10, and this will become 12 LCM is equal to 10, 3 VB plus VB is equal to 10. So VB will basically be equal to n multiplied by 12 divided by 4, so it will become 4143. So VB will be equal to 30 volts, right? And we know that the Thevenin voltage, right? Since there is no current through the 1 ohm resistance, so let's write it here also, that since there, let me adjust the paper, I hope it's visible now, yes. Since there is no current through 1 ohm resistance, right? means there is no current through the 1 ohms resistance. Therefore, Thevenin will be equal to VB equals to 30 volt. Right? I hope it's clear now. Now that we have found out the value of Thevenin, which is 30 volts, we need to calculate the value of R Thevenin also, that is the Thevenin resistance. And how we need to calculate it, we need to go to the main circuit now. This was our main circuit. And we need to turn off all the independent sources, right? So we should start writing turning off all the independent sources to find Thevenin resistance. Here you should note, you should remember that the voltage sources are turned off by replacing them with a short circuit, whereas the current sources are turned off by replacing them with an open circuit, right? So just look at the circuit and we will redraw it. 4 ohms resistance and 12 ohms resistance. This will be open, and this 1 ohm resistance. Finally we have the load terminals, right? This will be shorted and the current source will be open circuited now. Here let's name the resistances as R1, R2 and R3. Now you can see that R1 and R2 are in parallel. Why they are in parallel? Because they have two common points between them, right? So you can solve them in parallel. So during that we know that R1 is parallel to R2, right? So that makes it like R3, and this one will be R4, right? And R4 will be equal to R1 R2 divided by R1 plus R2. It will be 4 multiplied by 12 divided by 4 plus 12. So it will be 48 divided by 16, or it will be equal to 3 ohms, right? Now you can clearly see that R3 and R4 are now in series. So we can say that R equivalent R3 and R4 can be solved in series, right? So we can say that R Thevenin basically is equal to R equivalent is equal to R3 plus R4 is equal to 3 plus 1 is equal to 4 ohms, right? So I hope it's clear now. And the equivalent model, the equivalent Thevenin model will be that we have a Thevenin resistance plus minus 30 volts, VTH is equal to this. Then we have a series resistance, that is RTH is equal to 4 ohms. And then we have the load resistance, which is RL, right? So I hope there is no confusion in it. There is one more part of this question which is left here, and that part is pretty simple. That part focused on calculating the currents, and what values of currents that we had, the resistance values. So we had RL is equal to 6 ohms and RL is equal to 16 ohms and 36 ohms. So let's make 3 columns. RL, first of all we know that the current IL will be equal to V Thevenin divided by R Thevenin plus RL. So for RL is equal to 6 ohms, we can solve it. For RL is equal to 16 ohms, we can solve it. And for RL is equal to 36 ohms, we can also solve it, right? So this will give me IL is equal to 30 divided by 4 plus 6. So it will give you 30 divided by 10, 3 amperes, right? And the second part will give you 30 divided by 4 plus 16. So it will be 30 divided by 20. So this will give you 1.5 amperes. And the third part here, IL is equal to 30 divided by 36 plus 4. So it will give you 0.75 amperes, right? So this one is pretty easy. Let's have a quick overview of what we have done in this question so far. First of all, the question demanded us to find the Thevenin equivalent of the circuit. So the first two parameters that we needed to find out were the Thevenin resistance and Thevenin voltage. So we open circuit the load terminals. The open circuit voltage we calculated it with the help of nodal analysis, and that open circuit voltage was found out to be 30 volts, right? Here it is 30 volts. And in the next step, what we did was we just turned off all the independent sources. Luckily we did not have any dependent source. We will be doing the case of a dependent source in later part of this week, right? Then we solved the resistances. We found out the value of equivalent resistance to be 4 ohms. So we formed the Thevenin equivalent model, and based on that model we found out the value of load currents for different values. So I hope this is clear now. So now let's move on towards a second example of Thevenin's theorem. The statement for the problem is same, which says that, let me adjust the paper. Okay, the statement says that find the Thevenin equivalent for the given circuit, right? Let me draw the circuit also. Well, here in this particular question you can see one thing, that here the load terminals are already open circuited, so there is no need to open circuit the load terminals. So we will straight off move towards finding the Thevenin voltages and Thevenin resistance. First of all, we will go through the first of all we will find the Thevenin resistance, Thevenin voltage. The open circuit voltage is the Thevenin voltage.
which means that it is the voltage across this 6 ohm resistance, right? So here you can see that again which analysis method will be better. So we can apply mesh also, but here if there are two mesh and the current source is between two mesh, so it will become the case of a super mesh. You can apply it, no issue, but I am just avoiding it due to complexity. And again I will be using the nodal analysis method. This is my node A, this is my node B, and this is my node C, right? This is node B, D, which is the reference node, right? I have already calculated or found out the value of VA because how? Because VA is between a reference node and a non-reference node, which means that VA will be equal to 15 volts, right? And then let's applying KCL to node B. Fine. Now we are applying KCL to node B, and let's assume this current has I1, this one has I2, and right. So here we can see that the I1 current is entering the node and I2 current is leaving the node. And then we have a 4 ampere current which is also entering the node, right? So it will be plus I1, why plus? Because it is entering the node, minus I2, why minus? Because again it is leaving the node, and plus 4 is equal to 0. So we can simplify it as I2 minus I1 is equal to minus 4, right? And we know that how can we express I2 in terms of voltages? It is leaving from node B approaching node C, right? So it will be VB minus VC, right, divided by the resistance, which is 3 ohms. And how we can represent I1 in terms of the voltages? Minus, it is leaving node A, which is 32, minus VB divided by 3. 32 minus VB divided by 3 is equal to minus 4. And then we can write here VB 1 upon 3 plus 1 upon 3 plus VC minus 1 upon 3 equal to minus 4 plus 32 upon 3, right? So it will be VB 2 upon 3 plus VC minus 1 upon 3 is equal to, let me solve it with the calculator. How much value will it give? It's 32 divided by 3 minus 4, so it gives you a value of 6.67, right? And this will be our equation number 1. Then in the second step we need to apply KCL to this node C. I2 current is entering and I3 current is leaving. There will be no current through this branch. Why? Because of open circuit, right? So what we just need to do is write applying KCL to node C, and since I2 current is entering, it's plus I2, I3 is leaving, minus I3 is equal to 0, right? VB minus VC divided by 3 minus VC divided by 6 is equal to 0, right? So VB 1 upon 3 minus plus VC minus 1 upon 3 minus 1 upon 6 is equal to 0, right? and this will be equation number 2. Now if we have a look at the main figure, since we need to find out the value of Thevenin, and we see that Thevenin is equal to what? Vc, right? Because these are the same nodes. So we won't be using the value of Vb, and we will be directly calculating the value of Thevenin, which comes out to be like we will be solving equation 1 and 2, right? So we can write solving equation 1 and 2, Thevenin is equal to Vc is equal to almost 13.5 volts, right? So I hope that you people do not have any confusion in this. And now let's try to find out the resistance, right? Let's try to find out the resistance. And we know that for resistance what we need to do, we need to turn off all the independent sources from the circuit, right? So let's write it as turning off all the independent sources, in order to find our Thevenin, right? How the independent sources are turned off? Just a quick revision that the voltage sources are short circuited, whereas the current sources are open circuited. I realize that I am going a bit fast through this numerical, so after the completion of this numerical, I will repeat it completely, right? So no issue if you have any confusion. I will repeat it again after the completion, right? So this is where I have 3 ohm resistance. This branch is open circuited because of the presence of current source, and then we have a short circuited branch due to the presence of voltage source, 3 ohms, and then we have this 6 ohms, right? And these are our load terminals. So I hope that there is no confusion in this. And let's name these resistances as R1, R2 and R3. Here we can see that R1 and R2 are in series. So R1 and R2 are in series. So we can solve them. And the equivalent resistance will be like this, that here we have a value of R3 and this will be R4. Now you people can easily see that R4 and R3 are now in parallel, which means that we can solve them again. R4 and R3 are in parallel, right? R4 here, R4 here was equal to R1 plus R2 is equal to 3 plus 3 is equal to 6 ohms, right? And then we have this Thevenin is equal to R3 R4 divided by R3 plus R4 is equal to 6 multiplied by 6 divided by 6 plus 6, that gives you 36 over 12, and it is equal to 3 ohms, right? So our equivalent model will look like this. Just write it. The equivalent Thevenin model will be, and here is our equivalent Thevenin model, that we have a Thevenin voltage source with magnitude of 13.5 volts with resistance of 3 ohms, and this is what we have done here. See that we have simplified a comparatively complex circuit, which was this one, into a simpler circuit, which is this one, right? Here, this one, you can see. Now let me repeat the question and all the steps that we have done here, because I believe that we got through the question a bit fast. So let me repeat it. We were given this question, and we were given the objective of the question was basically to find the Thevenin equivalent for this circuit, right? And we can see that this circuit was a comparatively complex one with a load at this end, and then there were sources involved, right? So for whenever we are required to find the Thevenin equivalent model, basically we need two major parameters: the source resistance, the Thevenin resistance, and the Thevenin voltage. We know that the Thevenin voltage is the open circuit voltage. So we first decided to find out the Thevenin voltage. We can apply any technique, nodal, KVL, KCL, even superposition also. We can apply superposition, no issue in that. But we decided here to apply nodal analysis technique. VA we can easily find out because the voltage source is between reference node and a non-reference node. So the node voltage becomes equal to the source voltage. Then we applied KCL to node B. If you notice node B, we can see that current I1 is entering, I2 is leaving, which means plus I1 minus I2. 4 ampere is also entering, so its direction will be positive. I1 minus I2 is equal to minus 4. I1 is leaving from terminal A or voltage VA and flowing towards voltage VB, which means it will be VA minus VB, that is delta V, divided by the resistance, which is 3 ohms, right? So 32 minus VB divided by 3, and similarly I2 will be what? VB minus VC divided by 3, because it is leaving VB, it is approaching VC here. Just let me check one thing. I2 minus I1, okay, this will be plus 4, right? So please correct it. This will be plus 4 because it will be I2 minus I1. Yes, since I2 will go here, I1 will also go here, yes. So it will be I2 minus I1 is equal to plus 4, right? I1 minus I2 is equal to minus 4, I2 minus I1 is equal to plus 4. So this will become, start adding up, and it will become, let me solve it, 32 divided by 3 plus 4. So this is a calculation error from my side. 32 divided by 3 plus 4, so it becomes around 14.67 volts, right? So 14.67, right? And then we apply KCL to node C. If you can notice node C here, we will see that it only involves two currents. There is no current through the open path, because we know that the current through an open path is always 0. this current I2 is approaching, so its direction will be plus I2, and this one is leaving, so it will be minus I3, and here it is plus I2 minus I3, right? And VB minus VC divided by 3. Why VB minus VC divided by 3? VB, because current I2 is leaving from node B, so VB minus VC divided by the resistance 3, and similarly current I3 VC minus VD, which is 0, divided by 6, right? So VB minus VC divided by 6, and there may be a calculation error, but I believe that the answer is 13.5 volt. You people just need to verify. Okay, so once we find out the value of Thevenin resistance, the next step is to find out the value of Thevenin. Once we find out the value of Thevenin voltage, the next step is to find out the value of Thevenin resistance. As I have already repeated it previously, that it is not necessary to follow this sequence of steps. We can always first find the Thevenin resistance, and then go for calculating the Thevenin voltage, which you can also find in many books, right? So in order to find the Thevenin resistance, we need to turn off the independent sources. We have two independent sources here. This one is the 15 volt source, and this one is 4 ohms or 4 ampere source. 4 ampere source is turned off by open circuiting it, and 15 volts is turned off by short circuiting it. Now we can see that the 3 ohm resistance are in series, so we can add them, and their equivalent is in parallel with R3, so they are sorted, and we find the equivalent Thevenin model as this one. So right, I hope that this is clear now. In the next video, we are going to see the scenario of a dependent source, because up till now all the Thevenin questions that we have done, they simply involve independent sources. So in the next video, we need to check what the situation becomes when there is an independent, when there is a dependent source involved, right? So we will look at that.